In the second application, we will continue with imperfectly competitive markets, but we'll do a new example here. So the second application is about a Cournot model, but with advertising. Okay, so what is this Cournot with advertising? So you remember the standard Cournot model for two firms. So there are now two firms who produce Q1 and Q2 simultaneously, right, as opposed to sequentially. But think about a bit more elaborate version of the Cournot model, where firm 1 first decides an amount A to advertise. So firm 1 first decides advertising investment, let's say. Okay, A, denoted by A. Now that is observable to both firm 1 and firm 2. Once advertising is done by firm 1, then they both play a Cournot model. Okay, so that makes it a sequential move game. First firm 1 decides A is a continuous variable, and then firm 1 and firm 2 decides Q1 and Q2 simultaneously. What is the role of A? What would A do? A would change the demand function. So the demand function now is P equals A minus Q1 minus Q2. Okay, where this A is the advertising investment. Okay, so now A is a choice. Remember, in standard demand functions, we have been assuming this A to be some constant, right? So it was 12, for example, in the previous model. But now we are sort of giving it a twist, and we are saying that this intercept of the demand curve, which is given by this A, is actually endogenous. Endogenous meaning it is decided by one of the agents in the model. So in this case, firm 1 decides advertising, which in turn affects the intercept of the demand curve. So think about this case where, say, Coca-Cola advertises heavily about its own product, but that sort of generates more demand for soft drinks across the board, right? So it increases demand for Pepsi as well, right? So then Coke and Pepsi sort of decides its quantities simultaneously in a Cournot game. Okay, so this A, however, is decided by only one firm. Okay, just to sort of keep things simple, we will assume that like in the previous example, we will assume that production is costless. So we will assume that production is costless. So there is no cost of producing. However, we will say that advertising is costly. Advertising is costly. So the cost of advertising A is C of A, which is given by 2A to the power 3 by 81. So that's the cost of advertising. Okay. So from this you can then calculate the payoff, and then let me then write down the extensive form expression. So what is the extensive form expression of this game? So first, firm 1 chooses A, right? A is 0 to some positive number. It can be infinite, so let's make it A, 0 to infinity, any positive number. Then firm 1 and firm 2 decides Q1 and Q2 simultaneously, right? and both Q1 and Q2 are continuous strategies. So then for every choice of A, firm 1 chooses Q1, right? Q1 can be 0 to A at max, and firm 2 is also choosing Q2 from 0 to A. However, Q1 and Q2 are chosen simultaneously, right? So the way that I have expressed, this doesn't capture the game, because here it looks like that 2 can observe Q1 before choosing Q2. So I have to introduce now this information set in a continuous strategy, right? So now I am doing this. So the way to do this is to show here a dotted line like this. So this means that 2 doesn't know where it is located. 2 can't see Q1 when 2 is choosing Q2, right? To introduce simultaneous, to sort of demonstrate that it is a simultaneous move game in an extensive form format. Okay. So this dotted line is telling you that 2 has a non-trivial information set there. Okay, so 2 doesn't know what Q1 is when it is choosing Q2. So that makes the game's simultaneous move after A is chosen. But the entire game is sequential move, because first A is chosen and then they play a simultaneous move game. But after A, it's a simultaneous move game. Okay. And the payoffs, what are the payoffs? So payoffs is what? So again, production is costless. So the profit from the production is just the revenue. So revenue for firm 1 is A minus Q1 minus Q2 times Q1. But however, A is costly for firm 1. Investing in advertising is costly, and so that's the cost, as I've written in the previous page, it's this. For firm 2, it is just A minus Q1 minus Q2 times Q2, because firm 2 doesn't have any production cost and it doesn't invest in advertising. Okay, so this is the extensive form expression of the game, right? It's important to give this dotted line, remember, because this is a Cournot, not a Stackelberg. Okay, so how will we solve this game? Well, we can't do backward induction because there is, there are non-trivial information sets. So we will use the sort of more standard definition of subgame perfect Nash equilibrium. So we notice that this part of the game is a subgame, a proper subgame, right? So this is the initiating node. So basically for every possible Q1 there is a node for player 2, right? So, and all these nodes are in the same information set given by this dotted line. And all these are successors of the initiating node, right? So this is the initiating node, node, and these are all successor nodes. Right? So then all successor nodes are in an information set that doesn't contain any node that is not a successor of the initiating node. Okay, so then it's a subgame, proper subgame. So we will find out the Nash equilibrium of the proper subgame, and then we will incorporate that in one's decision making here. Okay, so that's how we will do it. So that will give us Nash equilibrium of the bigger game, and by ensuring that they are playing a Nash equilibrium in the subgame, it will give us the SPNE, right? Because SPNE means that they are playing Nash equilibrium in all subgames. Okay. So now this subgame is just the Cournot, right? Where A is a fixed number, correct? So that we don't that we know how to do. Okay, so let's just solve the Cournot, and the Cournot we know is a Nash equilibrium. So the Cournot equilibrium in that subgame will be the Nash equilibrium of that subgame, and we'll use the Q1 star and the Q2 star of that game and plug that into one's payoff function here to solve for A, which will be a decision making here. Okay, so let's do that. So let's solve for that Cournot. So solving for that Cournot is fairly easy. While solving for that Cournot, we can ignore the cost of investment here, this part, because this will only come into the play in the initial node, in the first node here. In the sub game, this doesn't play any. I mean, you can keep it around, but it will fall off in the first order condition. So in the sub game, forms play Cournot. Okay, so form 1 maximizes A minus Q1 minus Q2, okay, times Q1, sorry, so that's the revenue. Okay, so then this tells you the first order condition. If you take the derivative with respect to Q1, you get A minus 2Q1 minus Q2 equals 0. That gives you the best response function. Q1 equals A minus Q2 by 2. Okay, so that's the best response function of form 1 for any given Q2. Similarly, for form 2 will maximize A minus Q1 minus Q2 subject to Q2. If you apply the same first order condition, you will get the same result, that Q2 equals A minus Q1 by 2, right, by symmetry of the problem. So then the Cournot equilibrium is given by the value of Q1 and Q2 such that both best responses are satisfied, right? Because Nash equilibrium means they have to be mutual best response. So if I plug Q2 in Q1, so I get Q1 equals A by 2 minus half of Q2, which is A minus Q1 by 2, right? So that gives me 3/4 of Q1, right, is sorry, it's the entire, it's also A by 2, yeah, is A by 4. So that gives you Q1 as A by 3. Okay, if I plug into Q's best response, which is A minus Q1 by 2, if I plug A minus A by 3 by 2, I again get A by 3, right? So both Q1 and Q2 are A by 3 in the subgame. Okay, so basically you see it depends on A. It depends on positively depends on A, meaning the higher is the advertisement, so the greater Coca-Cola advertises about soft drinks, the higher would be the quantity produced by both Coca-Cola as well as Pepsi. Okay, so that's if the intercept is of the demand curve is higher, they'll both produce more because there's a higher price for any given level of production. Okay, so that's taken into account by the firm 1. Let me go back to the extensive form. So this, I have now solved this part. So now firm 1 knows therefore what is going to happen in the sub game, how the Cournot equilibrium will be played out. So when firm 1 chooses A here, it will know how it will impact both Q1 and Q2, and hence the payoff. So firm 1 will choose A to maximize its own payoff, knowing what Q1 and Q2 will be. Okay, so we know what Q1 and Q2 are here. So now firm 1's profit, let me write down the full profit, is A minus A by 3, so that's Q1, minus A by 3, that's Q2, times A by 3, that's the Q1. So that's the revenue. That's the revenue that's coming in the sub game, right, later from investing A. But it costs 2A to the power 3 by 81 to invest A in advertising. So that's the profit in the initial node that firm 1 can foresee that is coming for any given level of investment. So firm 1 chooses A to maximize this. So let me just simplify this. This is A minus 2/3 of A, so that's a third of A. So this is A square by 81. Okay, sorry, is this 81? That's not true. This is A squared by 9, right? Because it's A yeah, and then I have the 2A to the power 3 by 81. If I take A squared out, A squared by 9 out, I get 1 minus 2A by 9. Okay, I have to maximize this. What is the first order condition? So let me write down the first order condition. The first order condition is given by 2A by 9, right? That's the first term, 2A by 9. What is the second term? 6A squared by 81. 6A squared by 81, that equals 0. Now A can't be 0, so that basically means if I take A by 9 out, so let's take 2A by 9 out, so that gives me 1 minus 3A by 9 equals 0. So A is not 0, so that basically means 1 minus A by 3 is 0, which gives me A star equals 3. Okay, so that gives you the optimal level of advertising by the first firm. Okay, so then what is the subgame perfect Nash equilibrium strategies? Subgame perfect Nash equilibrium strategies is A star is 3, Q1, which depends on A, is given by A by 3, and similarly Q2 of A is given by A by 3. Notice in subgame perfect Nash equilibrium we specify strategies. So Q1 equals A by 3 is a strategy. For every A you have to specify, right, what are the actions. Remember the notion of strategy in a sequential move game is that you have to specify an action in every node that a player gets to move. So for every A, Q1 firms have to play a Cournot, right? For all possible A's, firms have to play a Cournot after observing that A. So those are different nodes. So for every node which is denoted by A, the strategy is to produce A by 3 by both firms. Okay, so that's the strategy. Of course, for in equilibrium, A star will be 3, which means Q1 and Q2 will be 1, right? But this is the general strategy. Okay, so this gives you the subgame perfect Nash equilibrium. Okay, So this is the sort of another example in the oligopoly structure. Let me move a little bit to something else, which is called which is an example of bargaining. Sorry, it's a third example. So it's the third example, and it's the example of bargaining. Okay. What is this example? So think about the ultimatum game that we were talking about in the last class. In that ultimatum game, the first player was making an offer. So first player had 100 rupees, and it was making an offer to the second player, and it was saying that P denoted how much player 1 wanted to keep for himself. So P ranged from 1 to 100, right? And the strategy for player 2 was only to accept or reject. Okay, so if player 2 accepted, the payoff would be P for player 1 and 100 minus P for player 2, and if it had rejected, the both will get 0, right? So that was the game, and in that game we saw that player 1 would keep everything for himself. Okay, so let me change the game a little bit. So suppose it is the case that now it's the same game. First one offers, one has 100 rupees to begin with. One offers a proposal to share that 100 rupees. So P1 says number P, where P is the money that he is keeping himself, and 100 minus P is for player 2. Player 2 can accept or reject. In case player 2 rejects, player 2 gets to make a proposal. Player 2 says, let me offer again a counter proposal. So that's the idea of bargaining. Let me offer a counter proposal of Q, okay, where Q is the money that's going to player 1. So both P and Q refer to the money that's going to player 1, just for simplicity, right? To sort of ease analysis. So Q is the money. Q, player 2 says, why don't you keep rupees Q, right? I'm rejecting this offer, and I'm counter offering to you. Why don't you keep rupees Q? Okay, so Q can also range from 0 to 100, and player 1 now can either accept or reject. So now player 1 can either accept or reject. If the player 1 accepts, player 1 gets Q, the counter offer, and player 2 gets 100 minus Q. If player 1 now rejects, player 1 both get 0. Okay, right? So this is the game. So now instead of just player 1 offering and 2 saying accept reject, I am allowing 2 to give a counter offer, and then 1 can accept or reject, and in case of rejection they both get 0. Okay, right? So since there are no non-trivial information sets here, everybody can see everything, which node all players are sitting on. Then we can apply backward induction, right? So we'll first start here and see what's happening in the terminal node. So again, 1 would accept as long as, if Q is positive, 1 would accept for all Q. If Q is 0, we say that again, to ensure this technical problem of continuity, let 1 accept for Q equal to 0 as well, because if Q equal to 0, then 1 is indifferent between acceptance and rejection. So acceptance is our best response. So one strategy here, one's strategy here is to accept for all Q, right? As long as Q is for any Q between 0 to 100, 1 would accept, right? Because the reaction will give him 0. Knowing that, what is the best thing for player 2 to do? We are doing backward induction. Knowing that player 1 is going to accept everything, best thing for player 2 is to keep everything for himself, to offer nothing. So Q equals 0. So 2's strategy here, 2's strategy is to offer 0, correct? After rejection. Now, knowing that, what to do here? Because player 2 knows that if player 2 rejects, player 2 would offer 0 and player 1 would accept. Correct? So if player 2 rejects, so now suppose player 2 is here, so what should be player 2's strategy here? What should be player 2's strategy here? If player 2 accepts, player 2 gets P, whatever 1 has offered. If player 2 rejects, player 2 will offer nothing, offer Q equal to 0 to the player 1, and player 1 will accept. It's a best response. It's for player 1. So player 2 would get 100 basically. If player 2 rejects, player 2 will get 100, and player and if player 2 accepts, player 1 will get P. So player 2, so if player 2 accepts, he gets P. If player 2 rejects, he gets 100. Correct? So player 2 strategy could be either to accept when P equals to 100 and reject in all other cases, or just reject every time. Okay, so both are fine. So basically player 2's can say that my strategy is to accept if P equals to 100, if 1 gives me 100, sorry, not P, I'm saying it wrong, because P is the money that 1 keeps for himself. So player 2 gets 100 minus P. So if 100 minus P is equal to 100, basically P is 0, so then I accept, and otherwise I reject. Well, that's one way of, that's one possible strategy. Or the other possible strategy of player 2 could be to say always reject, right? Because rejection will give him the highest pay of 100. In any case, whatever be the case, we know now what player 1 would do, because player 1 here, the only thing he can do is offer him 100, in which case, so basically keep 0 for himself, P equal to 0, because in all other cases player 2 is going to reject and get full 100, in which case he is also getting 0. So basically player 1 is indifferent between all offers, across all offers. If player 1 offers anything less than 100 to player 2, player 2 will definitely reject and get 100, in which case player 1 would get 0. If player 1 offers 100 to player 2 may accept or reject and get 100. In both cases player 1 would get 0. So player 1 would get 0 nonetheless. So basically one strategy, so here the point is, one is indifferent across all strategies, so which implies all are best responses. So if so then one may offer 100, may offer 50, it doesn't matter. The point of this exercise is that by allowing player 2 to counter offer, you completely change the power dynamics of the game, right? Remember, in the ultimatum game, the first player was keeping almost everything for himself, right? P was equal to 100. Now, and the payoff, basically payoff was P, which was equal to 100, and 2's payoff was 0. Now by allowing 2 to counter offer, you completely turn the table. Now you see by backward induction that 2 is going to get all the payoff and 1 will not. Okay, and by this logic you see what will happen if I, for example, change the game and say that, well, it doesn't stop after 1 rejects here. Here 1 again does a counter to the counter offer, like there is another game here, and then 2 can accept or reject, and then the game ends. Then again the table will be further turned back to player 1. Again you can show that 1 will keep everything for himself. Okay, so it depends on how many rounds of this offer and counter offer you allow players to make in this game. And basically what basically depends is who last makes the offer. If it's player 2 that is making the last offer in the game that we just analyzed, it is the case. So player 2 here makes the last offer. Whoever makes the last offer is the most powerful guy, right? Because then he gets to keep everything for himself in that last offer, and by backward induction would always like to reject unless he gets the last full payoff. Okay, the full share of the pie. So this is sort of an interesting setup of bargaining, where you see the person who makes the last offer takes the full cake away. Okay, so that's sort of another application. Let me stop and move to the other application in the next video.